In the field of service desk, one of the key roles is played by their support tickets, which are the driving force of their service desk business. One of the key indicators to evaluate the business performance is cost per ticket. This value shows how much does it cost to process a single ticket within the given service desk infrastructure. One of the ways to reduce the costs is to apply automatic classification using machine learning. In this video, we will discuss how this can be done, and we will use a recently introduced support ticket dataset by Phi-AI. Let's have a quick look at the dataset itself. So the dataset consists of 60 samples. Each sample is considered as a support ticket, and each ticket resembles a real support ticket. There are two main fields, which are subject and description. Subject is a short title for the ticket, while the description contains extended description of the issue. The third field is a key phrase which indicates key phrase in the ticket. You can split the entire dataset into access, user, and disk classes, and use this dictionary to have a mapping between key phrases and the classes. Finally, this dataset is designed to be used for unsupervised tasks like clustering, dimensionality reduction, etc., supervised learning like classification, and LLM-based tasks, embeddings, prompting, reg, and so on. Now, when we understand the content of the support ticket dataset, we can go ahead and load the data. This can be done in two ways. Besides for the HuggingFace hub, from where a dataset can be downloaded using the special library, it is also possible to load data from the dataset from original JSON files. There are three JSON files called access tickets, disk tickets, and user tickets. And these files are available at this repository. So once you download the file to your computer or to your environment, you should use a helper function, JSON to data frame, which will be doing the following thing. It will take a JSON dictionary, which contains data from the original file as an input, create the list of columns, and populate these columns with the data. Then it will create a data frame as an output. We will also add one more column, which is called label, based on the class of the dictionary which we use. So for access tickets, we will use the label 0. For disk tickets, we will use label 1. And for user tickets, we will use label 2. Then, since we have 3 JSON files and 3 corresponding dictionaries, we will run the loop through all the JSON dictionaries, and we will concatenate all the data frames in one unified data frame. And finally, we will get the resulting data frame, which has subject, description, key phrase, and label. A second way of loading support ticket dataset is from HuggingFace Hub. For this, we need dataset library and particular load dataset module from that library. And using the load dataset module, we can get support tickets dataset from Phi-AI info support tickets. So here you can see how the dataset looks like. Again, we will need a helper function to convert a dataset into the data frame. In this case, a single sample contains 3 different keys. We will again collect all the keys in a single sample, run through all the samples and populate the columns which correspond to the key names, and then we will also add extra column which is label. And finally, we will pack it into the data frame. In this case, however, since all the records are contained in the single dataset, we don't need to concatenate different data frames, but we'll get a single data frame as a result immediately. In order to do the labels, we will also need a label dictionary. So first we define a function, and then we will define a label dictionary as follows. So grant access, revoke access, and access profile will have label 0, disk space, disk full, and disk error will have label 1, add user, delete user, create user, and modify user will have label 2. So if we identify these key phrases in the key phrase field, we will assign corresponding labels accordingly. So let's run dataset to data frame, and here we will have a resulting data frame. Now, let's do a sanity check, and we compare the dataset derived data frame, a df underscore dataset, and data frame tickets underscore df, which is obtained by converting multiple JSON dictionaries into data frames and concatenating those data frames. So here we will run several tests. First, we will confirm that shape of those dictionaries are the same, that column lists are the same. In other words, these data frames have the same columns. Here we confirm that these data frames are the same. Now let's do a data processing. Again, let's have a look at the first 5 records on tickets underscore df. We will use this data frame as both data frames are the same, so we select tickets data frame for the further analysis. Now we'll load a list of stop words. For this, we will import an LTK library and obtain stop words from an ltk.corpus. Next, we will load a lemmatizer. Lemmatizer is a method to convert different forms of the same word into kind of a basic form of that, or a root form, which is a little bit different from a stammer and more effective, but works in a similar way. So instead of a stammer, we will use lemmatizer. Again, we will load a WordNet lemmatizer from an ltk.stem module, and we'll define lemmatizer as a WorldNet lemmatizer. Here you can see the result. The word corpus, which is a basic singular form of the word, is a result of converting word corpora, which is multiple of corpus, by a lemmatizer. Also, word better, which is comparison degree of word good, is converted into word good. And here you can see that you can use additional parameter as a part of speech, and here provide a key A, which corresponds to adjective. Now I think you get an idea of what lemmatizer is doing. Next, we will create a preprocessing routine, and we call it preprocess text. So first, this function will take string as an input, and it will have 2 additional positional parameters. Stop words, it should be a stop word list, and lemmatizer, it should be a lemmatizer. The first transformation which we will do is to drop punctuation signs, and then we will convert a string into a lowercase. Next, if stop words list is defined, we will go ahead and drop all the stop words on the string s. Finally, if lemmatizer is defined, we will go ahead and lemmatize each single word in the same string. By the way, here I'm using variable text, which is a copy of variable s. And then text variable is an output of this function. So we will have our string to be cleaned from punctuation sign, to be cleaned from the stop words, and all the words in the string will be taken to its basic form. Let's see an example of how this preprocess text function works. First, we will only provide a stop word list, and in this case, particle 2, which is a part of the stop words, should disappear. Second, we will also apply a lemmatizer. In this case, the particle 2 should disappear as in the previous example because we provide a list of words. Also, word documents, which is a multiple for document, should be converted into a singular basic form, which is document. So the helper function works as expected. Now let's go ahead and preprocess the data frame. For this purpose, we will select description column and subject column, and we will preprocess each column separately using apply method of the column and the lambda function as follows. Now let's run these 2 transformations and inspect the resulting data frame. So here you can see that we have 2 additional columns, preprocess subject and preprocess description. If you look at the description, we can see that all letters are now lowercase letters. Particle 2 has disappeared. Word documents is converted into its single basic form, document. And we also have no punctuation signs. This concludes data preprocessing part. And now let's dive into analysis of our dataset. So we start off embeddings and dimensionality reduction. In order to be able to work with words from natural language and apply various algorithms to word sentences and any language structures, we first have to convert words into numerical vectors. In order to do so, we will apply a method called embeddings. Embeddings allow to encode words, combination of words and sentences of natural language into n-dimensional numerical vectors. I have a special video where I briefly describe the concept of embeddings and the sentence transformer model, so please check a link in the description below. So we will start off importing sentence transformer library and then load all MPNet base version 2 embeddings model. Next, we convert a preprocessed description column of tickets data frame into the list and apply encode method to our sentences, preprocessed description, and embeddings should contain multidimensional or n-dimensional vectors. Let's investigate the shape of those vectors. So first of all, we can see that there are 60 inputs in embeddings. Each input corresponds to a single sentence. In total, we have 60 tickets. This is exactly the size of our data set. And then numerical vector has a dimension of 768. All MPNet base P2 model belongs to bird base model family. And for bird base, there is a fixed dimension for embeddings, which is 768. Along with the base family, there is extended branch in bird family, which will have embeddings of dimension 224. In this case, we can go ahead and do analysis with all 768 dimensions. However, for the purpose of this case study and to be able to visualize these embeddings, we will boil down 768 dimensions into lower number of dimensions using dimensionality reduction technique. In this particular case, we will use principal component analysis and we input principal component analysis from Scikit-Learn. We reduce 768 dimensions into 2 dimensions, and before applying dimensionality reduction transformation, we will copy original embeddings into some temporary variable in order to be able to reverse if something goes wrong. And then we apply Phi-AI transformation. So now have a look at the variable x transform, which contains embeddings boiled down to 2 dimensions. Now, finally, let's plot these embeddings in 2-dimensional space. So here we can see how all the sentences across all 3 classes are distributed in 2-dimensional space. We can see that this group of sentences forms a very compact structure, which is called cluster. And we can also see that the left-hand side of the image can be also split into 2 clusters, the top and the low one. Let's go ahead and apply k-means clustering for embeddings of description column. And as we have 3 classes in the original dataset, we will apply 3 centroids, and these are preset values. In this particular study, we just go ahead with these values, but in more general case, there will be multiple runs in order to understand which is the better initializations for the cluster centroids. So let's plot cluster centroids versus the data points in the same chart. So here you can see we have 3 clusters: red cluster, blue cluster, and green cluster. Also, before we dive into k-means clustering analysis, I will apply some auxiliary variables. So clustering time is a dictionary which will store the structure of clusters or lists which sentences belongs to which cluster at each iteration. In our case, iteration will contain 2 steps: cluster assignment step and centroid update step. You can learn about these steps in my video about k-means clustering for embeddings. You can find the link. So centroid in time is a dictionary which will have an index of a cluster as a key, and content will be list. This list will contain values of centroid for a given cluster at each iteration. Finally, we will have one more auxiliary variable, centroid dict in time, which is a dictionary, and for each iteration, it will store entire dictionary of centroids. And also we will introduce iteration -1, which will contain originally initialized value of centroids. This way, we will be able to track the values of centroids and the cluster structure across the iterations. In this example, we will apply 3 iterations, and as I mentioned, we will do 2 steps during each iteration. First step will be cluster assignment step, where we distribute data points across the clusters by computing the Euclidean distance and selecting the minimal value between a given data point and each of 3 centroids. So the sample will be assigned to the cluster which corresponds to the centroid with minimal distance from a given data point. And then second step for each iteration is centroid update step. In this case, a new centroid is computed as a mean value for all the data points assigned to a given cluster. So let's go ahead and run k-means clustering, and let's visualize the final clusters. You can see that for cluster 1, we assign these sentences. For cluster 0, we assign these sentences. And for cluster 2, we assign these sentences. Now let's have a look how cluster 0, 1, and 2 correspond to the previous coloring mapping of red, green, and blue. And you can see how we actually assigned sentences to the clusters by color. So as we observed in the visual analysis, the sentences in the right-hand side form an individual cluster, and then sentences in the left-hand side, they are split into two clusters, the higher cluster and the lower cluster. Now let's see how the labels of the sentences are distributed across clusters. We can see that cluster 1, most of the sentences belong to class 0. We have only 3 sentences which belongs to class 2. For cluster 0, most of the sentences belong to cluster 2. There are only 2 sentences belong to class 0. And finally, in case of cluster 2, all the sentences belong to class 1. So what are these classes? Cluster 0 is a red cluster, cluster 1 is a green cluster, and cluster 2 is a blue cluster. And we can see that in the case of cluster 2, everything is coming about the disk space. So this is our disk class. In case of cluster 0, most of the sentences are about users. So it's new user, new admin user, and so on. So this is class 2, class users. And finally, cluster 1 is mainly about access. It mainly represents class 0, which is access class. However, these mappings are not perfect. We can see here and there in cluster 0 and cluster 1 inclusions of the elements from the different classes. So we can compute how the classes are actually polluted with inclusions of the different classes after the k-means clustering. Here you can see that in case of cluster 0, there are 10.53% of sentences from access class, 0% of sentences from disk class, 89.47% of sentences from the user class. In case of cluster 1, we have 85.71% sentences from access class, 0% of sentences for disk class, and 14.29% of sentences from user class. Finally, in case of cluster 2, all the sentences are coming from the disk class. Now let's see if we can do better. And for this purpose, we will use now n-grams or pairs of words. So in order to collect the pairs of words, we will apply combinations from iter tools. So we have a sentence, approve user access to confidential documents. So what would happen? These combinations function will collect all the pairs from the very beginning to the very end of the sentence. Let me show you an example. So first we take word approve, and then they take all the pairs of these words with all the consecutive words. Approve and user, approve and access, approve and to, approve confidential, and approve document. And we do it for all the words in the list. So in order to collect unique pairs, we will use this auxiliary function. We will also define two dictionary, pair dictionary, which will contain a particular pair and its frequency in entire dataset, and pair origin, which will contain pair of words and the sentence this pair has been extracted from. Run this code and have a look at the pair dictionary and origin. So the pair dictionary should contain frequencies of a given pair occurrences. So we can see that grant user appears twice, grant access appears 7 times, and so on. Pair origin will give us a list of sentences a particular pair appears in. So you can see that grant access appears in sentence 0 and sentence 3. Grant access appears in sentences 0, 3, 6, 9, 12, 15, 18, and so on. Now let's do in-depth analysis of the pairs. First, we will list all our pairs, and we see that we have 60 sentences, which is the size of the data set. And then from these 60 sentences, we have collected 579 pairs. So it will be not useful to use all these pairs because they have different frequencies and they do not bring equally useful information. So we will need to filter out and select most important pairs. For this purpose, we will sort the dictionary of pairs by the frequencies. So after transformation, we can see that our pairs are ranked in the descending order, starting from the most frequent pairs and going down to less frequent pairs. We know the ideal pairs for each class, which are grant access, revoke access, access profile, disk space, disk error, disk full, add user, delete user, modify user, and create user. Essentially, these are our key phrases assigned to each data sample. So let's have a look how these key phrases are distributed inside the dataset. So grant access appears 7 times, revoke access appears 7 times, access profile appears 6 times, which is 20 in total. Disk space and disk error appear 8 times each. Disk full appears 5 times. So and then add user appears 5 times, delete user appears 5 times, modify user appears 5 times, and create user appears 5 times. So now let's select the most informative pairs and see what would be our shortlist. We will apply threshold 4, so everything which is equal to 4 or below, all those pairs should disappear from the shortlist. So now the original dictionary contains 579 pairs, and the shortlist contains only 15 pairs. Let's have a look. So we stop at modify users. Indeed, modify user is the last pair with frequency 5. Everything else is less than 5. So now let's compute coverage. We want to understand how many sentences contain these pairs. In other words, from how many sentences we collected these pairs. Because all these pairs do not come from all 60 sentences, then some of the sentences will be overseen and there will be no pair associated with that, so it will follow our analysis. So we compute the coverage as a ratio, number of sentences which contain the collected pairs versus total number of sentences. So in our case, coverage is 100%. However, if we apply more aggressive threshold, so for example, we'll say threshold is 5, our shortlist will become even shorter, and the coverage value will become 78.3%. If now we apply less aggressive threshold, let's say 3, we will see that our shortlist increases from 8 to 20 to 22, and our coverage is becoming again 100%. So in this case, threshold 4 is optimal as it represents the border between the coverage and a number of necessary pairs to represent all the sentences. Then we have pairs of words with their coverage of 100%. We'll go ahead and apply clustering analysis for pairs or 2 grams, which we have just collected. Well, first, let's review our pairs. We have collected 2 n-grams, which allow us to describe all the 60 sentences in our dataset, let's apply k-means clustering for the pairs. We'll use the same sentence transformer library in order to produce embeddings, but before, let's have a look at the pairs themselves. So we have 15 pairs in total. Now let's create embeddings using the same model as in the previous case with entire sentences. And we will also apply the principal component analysis to reduce dimension from 768 to 2. And now we can visualize our pairs. We can see that in this case, the clusters are even more separable and more compact. So we see that in the right-hand side, we have a very nice cluster, which corresponds to the disk. On the top, we have a cluster which corresponds to access, and in the lower left part, we have a cluster which corresponds to user. Now let's initialize our centroid and check how our centroids are related to the points. Clustering procedure and the clustering code is similar to the previous step, but let's do one more additional analysis. Let's check how centroids evolve across the 3 iterations of k-means clustering. So we can see that we start from the original positions, and then pretty much quickly centroids converge within the clusters which we expect. Finally, let's visualize assignment the pairs to different clusters. And we also can show the size of each cluster by drawing a circle around each cluster. Finally, let's see how the pairs was distributed across the clusters. So we can see that cluster 2 contains user access, profile, add user, delete user, create user, and modify user. In this case, cluster 2 is becoming a user cluster. Well, user account is also belongs to user cluster. Update profile might be related to a different class. In case of cluster 0, everything is related to the disk. And in case of cluster 1, everything is related to the access. Now let's assign cluster pair label to each of the pairs. You can see that in this case, the distribution of labels across the clusters using the pairs of words is perfect. So each cluster contains only pairs from a given class. Now let's use this information in order to label our original examples. As mentioned at the beginning of the video, labels which we assigned to our sentences are used for illustrative purposes. These are not actual labels. We do not consider a dataset to be a labeled dataset. In reality, the support tickets will also come without any prior label. So we have to assign labels to these tickets somehow. One of the ways is used to some unsupervised methods, for example, k-means clustering, which we have already done, and use the results of the clustering to assign labels to the original data. So now let's go ahead and create the tickets labels. So now that we have a mapping between pairs of words and clusters, let's assign labels to entire sentences in our original dataset. To do so, we will use a helper function, create label from cluster. And what this function will do is it will take a sentence from our data, which will be a preprocessed description sentence. It will split it into individual words, and then we will compare if a given pair from our clusters can be found in that particular sentence. So if we find a pair in a given sentence, we will assign a label which corresponds with that pair to a given sentence. Let's run this. So you can see that for some sentences, we have a single pair found in that sentence. However, for example, sentence 5, we have 3 pairs found in that sentence. So we will find a pair from cluster 2, and we will find a pair from cluster 0. So this creates an ambiguity because we can find pairs from different clusters in a given sentence, and we have to resolve the situation. So in this case, you can see that there is only one pair from the second cluster, while there are two pairs from the first cluster. So we will compute a frequency of the pairs from each cluster and assign a label of the most frequent cluster. So in this case, for sentence 5, we'll select label 0. For sentence 8, which also has multiple entries, we will have also label 0. However, there are controversial cases, for example, with sentence 57, when we have pairs from both cluster 2 and cluster 0 and their frequency are equal. In this case, we will voluntarily select the first label. However, in a real case, you can go ahead and design more sophisticated logic, if you will. So let's go ahead and implement this logic, which I have just explained. In order to extract the most frequent label, we will compute the unique labels and build a histogram of these labels. And then we will take the most frequent value from the histogram and get the associated label. The result of this operation will be sent labels dictionary. Here we have a sentence index and a corresponding label assigned using this logic. Finally, we'll generate a list of predicted labels, getting the list of sent labels dictionary values, and we will create a new column in our tickets data frame. The new column is called gen labels, and this will be our generated labels. And here is our resulting data frame. You can see that true labels, which we assigned during the dataset load procedure, almost perfectly coincide with generated labels. The only case of mismatch is with sentence 57, where this sentence is assigned to class 0. Now when we have our label dataset, let's go ahead and add some classifiers. First, we will import some auxiliary functions which will help us to understand the results of classification. So we will do the confusion matrix analysis and classification report. Then we will apply the sentence embeddings again, and we will use train test split, an auxiliary function from Scikit-Learn, in order to split our entire dataset into train and test subsets. Now we will use logistic regression module from Scikit-Learn and train our logistic regression classifier. Here we will generate a prediction using the train classifier. So these are all labels for the test set. And here we can produce classification report and confusion matrix. So in our case, we have three classes: access, disk, and user. And we can see that for access class, one sample is misclassified as user, while for other classes, disk and user, we don't have any errors. Also, the results of our classification report is in this data frame. So let's investigate the content of the data frame. We can see that for each of the classes, precision, recall, F1 score, and support are computed. You can see the overall accuracy of 95%, and we can see the average values for each of the metrics. So we can see that weighted average for precision across all three classes is 95.71%, for recall 95%, and F1 score is also 95%. So this is pretty simple data set. So let's go ahead and check another classifier. In this case, we will use deep neural network. And to implement the deep neural network, we'll use TensorFlow library. So we will import TensorFlow and import some auxiliary components like sequential structure, types of different input layers, type of loss function, which will be categorical, cross entropy in this case, and type of optimizer. We'll select Adam. And finally, we will use auxiliary function to categorical in order to convert our labels to the categorical labels. So first we convert our labels into categorical labels. And you can see that in contrast to one-dimensional labels, the categorical labels are three-dimensional one-hot vectors, where one corresponds to the actual class this label belongs to. Then next, we create a small and simple forward neural network. We will use a sequential structure of the model. We will use the input with original size of 768. We don't do any dimensionality reduction in this case. And then we apply a fully collected dense layer of size 256, followed by fully connected dense layer of size 128, 64, 32, and finally we will apply a softmax layer, which is our classification layer, in order to produce a probability distribution for a given sample. Finally, we will combine a model using categorical cross-entropy loss function. We will use a matrix's accuracy and optimize its ADA. Before we train the model, we will assign number of epochs and the batch size. So number of epochs will be 50 and batch size will be 128. We will initialize the model and print the model summary. So this is our model. Then we also import model checkpoint, which will help us to say the best model. This module is imported from TensorFlow keras called X. Define our checkpoint to save a model into the best model file. The monitoring metric will be validation accuracy, and we will save the best model. So once our validation accuracy exceeds the existing value of validation accuracy, we will update the model by providing the new best model. So now let's train our model using the theta component and our xtrain and ytrain cat as the training set, and xtest and ytest underscore cat as our validation set. We will apply number of epochs, batch size, and as a callback we will use a checkpoint, and we will print out the entire training process. So this is a very simple model, so we can do it on nearly real time. So let's have a look at train and validation accuracy. You can see that validation accuracy is very high and is very close to the train accuracy, so we do not expect any overfitting of the model. Now let's generate predictions. So first we will load our saved best model. Then we will use our xtest values in order to produce test predictions. And then they will use test predicted labels in order to generate classification report and compute confusion matrix. The results of classification report will be saved into df_nn. So let's run this code and see what results we have. So in the case of test set, for all three classes, all the input data points, for all the samples are classified correctly. So confusion matrix is fully diagonal. And our classification report also indicates that precision recall and F1 score are 1 for all the clusters, and the weighted averages are also 1. So this concludes the case study for ticket dataset. I hope this was interesting. This actually represents a very accurate replica of analysis of support tickets in real. Of course, each stage will be much more complicated and will have a lot of more granular details. But in principle, these are the main steps how you can take unlabeled data set of natural language corpus, convert it into labeled data set using some unsupervised learning techniques like clustering. And finally, you can train a classifier on your new label data. So in the end, it should allow you to automate ticket classification process and reduce the time per ticket analysis and consecutively reduce the cost. So thank you very much. See you in the next videos. All the materials mentioned in this video, including repositories and videos, you can find the details in the description below. Thank you.